All right, in this lecture, let's discuss the relativistic derivation of kinetic energy. Now, armed with our definition of relativistic momentum and the fact that we can compute the force from the change in momentum, we can do this derivation. And then we'll do some examples afterward too. So, we're going to retain our usual definition for force. Force is a change in momentum, dp dt. But we're going to use the relativistic definition of momentum that p vector is gamma mu, where u is the speed, or the velocity, I should say, of that particle in that reference frame. And gamma is the associated shorthand for 1 over square root 1 over 1 minus u squared over c squared. So this is our definition of force. Now, let's also discuss something else from Physics 1, or Introductory Physics, which is the work-energy theorem, that if you do work on an object, that changes its kinetic energy. In other words, the change in kinetic energy from the initial state, say 1, to the final state 2, k2 minus k1 is delta k. So if I apply work, which essentially is like force times distance, that will increase the kinetic energy of that object. So we're going to use these concepts to be able to work it out using relativity and our new definition for momentum. All right, so let's calculate the work done to move an object from point 1 to point 2. So I'm going to draw it over here on the right. So I'm starting at point 1. I want to end up at point 2. But there's a force involved, and I just show it at some arbitrary direction. So F vector is pointing up and to the right. And we're going to calculate the work done by that force to move the object from position 1 to position 2. That work done will increase the kinetic energy as you go from 1 to 2. And what is work? Well, that's force times distance, but in vector form, it's a scalar dot product, F dot ds, where ds is an infinitesimal unit of length along our curved path from point 1 to 2. It may be curved. I'm just assuming an arbitrary shape, so it may be curved. And F dot ds is the projection of the vector F onto that axis or direction of ds. Now ds itself, that infinitesimal length, can be thought of as the velocity, times an infinitesimal time, right? Velocity is dx dt, in the x direction anyway, so dx dt times dt is just dx. So this ds, this arbitrary infinitesimal length in whatever curved direction we're going, is the velocity at that point times dt. Okay. So our change in kinetic energy, if we plug in our relativistic definition of momentum into our definition of force, force is d dt of gamma mu. I put d dt gamma mu for force, and that's dotted with ds, which I'm going to put in u dt. Okay? All right, so that's just plugging in for our definition of work using our definition for momentum and force. Now, what we can do here is we can bring the mass obviously outside the equation, or outside the integral, I should say. Let's bring the dt up in front of the derivative. And so if I do that, I get the equation down below. I've pulled the mass out front of the integral. I move dt in front, and I have dt times ddt, the quantity now gamma u, where u is the velocity vector. I pulled the m out, remember, dotted with u. And so I can kind of think of it as these dt's canceling here and here. And what I'm left with is the integral mass times the integral from 1 to 2, point 1 to point 2 of d of gamma u dotted with u. Okay? So that's essentially what I'm doing here. And let's remember that equation there. We're going to move it on to the next slide, okay? And continue on from there. All right. But as we go from position 1 to position 2, let's start from rest in this example. Let's start with an initial kinetic energy of 0. And so the final kinetic energy, k2, will just be k. That'll be the value we achieve once we've gotten to point 2. And let's integrate that function we had by parts. So this here on the left was the expression we left with, d of gamma u dotted with u. All right. And then we're going to integrate that from rest. So the speed would be 0, the velocity would be 0, and gamma times the velocity in the final point would be gamma u2 here. And we can integrate this by parts, because I've got a piece here that depends on u and a piece that depends on the differential of some vector, d gamma u. So in integrating by parts, this is like the, if I write it here, by integrating by parts, this is kind of like the u term, and this is the dv term. But I don't want to just not mix it up with velocity at this point. And so that's going to give us uv in integrating by parts here, and then it'll be a v du here when you integrate by parts. I'm just kind of showing these roughly so if you remember how to integrate by parts. Anyway, so what we called dv is d of gamma u. So v itself is gamma u. So the uv term is that gamma u times u. It gives me gamma u squared. And then there was a mass out front, so I have to keep the mass. And that's evaluated from gamma u2 is from 0. So I just get the gamma m u2 squared out front. But then I have to subtract off by integrating by parts the integral of v du. And so v was gamma u, so it's gamma u dotted with what is du? It's d, well, du is be d of just u, so it's du. So it's this part here. So that's integrating that equation by parts. Okay, so let's do that. I'm going to retain the gamma mu2 squared. That was the first term in the integration by parts. And now what have I done? There was a scalar dot product of u vector dotted with du vector. But wait a minute. U vector and du vector are in the same directions. They're parallel to each other. So that dot product just becomes a multiplication and it becomes u du. And what is gamma? That was shorthand. That's 1 over the square root 1 minus u squared over c squared. Remember, this is the gamma that goes with the velocity in that reference frame. So this is the square root in the denominator. And I'm going to integrate now in terms of du from u to the final velocity u2. That is the velocity at point 2. All right, now I have a different integral to do. We can do this integral itself with this radical here by doing a substitution. We can put a new variable inside the radical and integrate this by substitution. Or you can just go ahead and look up such integrals by integral tables or whatever program or application you may have. And so the final result will be here on the right. I still keep the gamma mu2 squared term. That was the very first term by integrating by parts. This integral, the second one that was subtracted off, becomes this expression here. It's mc squared times the square root of 1 minus u squared over c squared, evaluated at the endpoints from 0 to u2. You could see that if I took the derivative of this radical, this is something to the 1/2 power. I'm going to end up with something to the minus 1/2 power. So indeed, this integrated must give me something like the radical here. All right, let's try to simplify this down. Keep the gamma mu2 squared. I have now plugging in u2 here, I have mc squared times the square root of 1 minus u2 squared over c squared. That's this piece here. But when I plug in and subtract 0, I'm going to get mc squared times, minus mc squared times square root of 1 minus 0, which is the square root of 1, or just 1. So we get a minus mc squared here. All right, well, let's kind of collect terms here. This radical square root 1 minus u2 squared over c squared is kind of like 1 over gamma. So if I pull out a factor gamma in front of all this expression, I would have to raise the power by 1/2. So this 1 minus u2 squared over c squared multiplied by gamma, which is dividing by square root of 1 minus u2 squared over c squared, would leave me the square root of 1 minus u2 squared over c squared. So I can pull out the gamma here, provided I raise the power here from 1/2 to just 1. I pulled the gamma also out front of the first term, so instead of gamma mu2 squared, it's gamma times mu2 squared. And then I have mc squared times equality 1 minus u2 squared over c squared in bracket, and then I'll leave the minus mc squared there at the end. But now what we can see is that this mu2 squared term here in the first part in the brackets, when I take and multiply mc squared times minus u2 squared over c squared, gives me minus mu2 squared. So that term cancels with the first term. And so I just have gamma times mc squared minus mc squared. So my formula gets quite compact now. I have kinetic energy is gamma minus 1 quantity times mc squared, where gamma is 1 over square root 1 minus u squared over c squared. So that's it. We've just now derived by using the concept of work and the work energy theorem to increase the kinetic energy based on that work to get a relativistic expression for the kinetic energy. Kinetic energy is gamma minus 1 mc squared. All right, so that's one more important result coming out of special relativity. But let's pause a moment and let's contemplate a bit what we just derived, this expression for kinetic energy. That kinetic energy, K is gamma minus 1 mc squared, doesn't look anything like, at first impression, like the non-relativistic expression K is 1/2 mu squared. Again, u is the velocity of the particle. How do these two relate to each other? They don't look anywhere near the same. In fact, they should seamlessly match for speeds much less than the speed of light. For u, much, much less than c. So when I write two less than signs, it means much less than. This is kind of referred to as a correspondence principle. And we want to talk about our expression corresponding to the classical results of physics, classical physics. Or put another way around, it's not that Isaac Newton was totally wrong in his formulation of physics and his expression for kinetic energy, and that Einstein is now the one who's right. It's just that the laws of physics need modification when you have speeds approaching the speed of light c. But if you're at much less than the speed of light, Newton's formula still works quite well, and we wouldn't be teaching you introductory physics before this course if it weren't working out right. All right, so how can we see that these match up? Well, let's try a binomial expansion, or at least in general a Taylor expansion. We have gamma as our factor, which is 1 over the square root 1 minus u squared over c squared. But written as a binomial, it's 1 minus u squared over c squared to the minus 1/2 powers. If I do a Taylor expansion for small u, this is going to be approximately 1 plus, well, actually be minus, then pull down the power, minus 1/2. So it'll be 1 plus 1/2 times u squared over c squared, plus higher order terms. It'll be u squared over c squared squared, and u squared over c squared cubed, and so on. But the first leading two terms are 1 plus this 1/2 u squared over c squared for gamma. And let's plug that into our expression for the kinetic energy. Kinetic energy in relativity was gamma minus 1 mc squared. So that's gamma minus 1 means I subtract the 1 here off, and I have just 1/2 u squared over c squared times mc squared. The c squareds cancel, right? I just have 1/2 mu squared. Aha! There it is. They do match. When I have small u much less than c, and I do a Taylor expansion, my relativistic form for the kinetic energy matches up with the non-relativistic form, and that's good. Right? That's what we want to see. That means there's a correspondence to classical physics in the regime where Newton's laws are valid, or the non-relativistic results. All right. Now that we have shown that, in fact, it's the same kinetic energy, at least at low speeds, that we've always been using, let's see how these two definitions, the relativistic and non-relativistic, change as the speed gets larger. So I've made a table here of the kinetic energy versus the speed of an object. And let's, for simplicity, let's consider an object with a mass of 1 kilogram. So the m is just 1 in SI units. And let's calculate the kinetic energy in joules for such a mass using both the Newtonian and relativistic mechanics version of the kinetic energy as a function of speed. So this is a table. I have speed increasing downward. This is the kinetic energy you would get using Newton's formula, p squared over 2m essentially, or 1/2 mu squared. This is the relativistic version. K is gamma minus 1 times mc squared. And this is the ratio of the relativistic kinetic energy over the Newtonian version of the kinetic energy. All right, if we take speeds that look small, 4 times 10 to the minus 5 times the speed of light, well, it's not really that small. That actually is the escape speed to leave planet Earth. So, it's still pretty fast. But in terms of relativity, this is a small fraction of the speed of light. We get essentially the same value for the kinetic energy, and the ratio is 1. Okay, so there's not much difference with the relativistic definition. Now let's go to a value of 1/10 the speed of light. So now you're going pretty fast, 10% speed of light. But still, at least to 2 decimal points, 2 significant figures, I don't see much difference. If I calculate out to 4 significant figures, the ratio, I see them a little bit under 1% more for the relativistic definition. In other words, at 10% the speed of light, the relativistic kinetic energy is almost 1% larger than the Newtonian definition. Now, let's go to 50% of the speed of light. Okay, now we're really cooking, right? Now I start to see some differences here. The relativistic form is 1.4 times 10 to the 16 joules. The Newtonian form is 1.1 times 10 to the 16 joules. There is a difference, and the relativistic form is 24% larger. So to get that same speed, I had to add 24% more work to get to that kinetic energy corresponding to that speed. All right, let's go to 90% the speed of light. Now I see a much bigger difference. They're 3 times different. It takes 3 times more energy to reach that speed using the relativistic form of the kinetic energy. In other words, the relativistic kinetic energy is 3.2 times larger than the non-relativistic form. All right, you want to get even closer to speed of light, 99% the speed of light. Well, now the relativistic form of kinetic energy is 12 times larger, 12.4 than the Newtonian non-relativistic formula. What about 99.9% the speed of light? Well, now it's 43 times more energy needed from work to get that kinetic energy in the relativistic form. And what if we want 99.99% the speed of light? You're really getting close. Well, now I'm getting a big difference. It's over 141 times larger in the relativistic case. So obviously, as I get very close to the speed of light, the ratio gets very large. Now, by the way, I forgot to say, this ratio of the relativistic kinetic energy to the Newtonian, how did I get these numbers? Well, we can use the expressions we had before, but it boils down to this: 2 times gamma minus 1 over beta squared. What is beta? I'm introducing a new term here. Beta is shorthand for just this v over c quantity. It's kind of the dimensionless velocity relative to the speed of light. So this speed here, if I remove the c, that would be beta. But that's the expression if you're interested in how to calculate this ratio, and you can do that as homework on your own to figure out that indeed the ratio of the relativistic form of kinetic energy to the non-relativistic is this ratio here. And one thing you can conclude from this exercise of trying to get ever closer to the speed of light, notice that if I get to 90% the speed of light, then to 99.9% speed of light, the Newtonian kinetic energy is not changing much, right? It went from 3.6 to 4.4 to 4.5 times 10 to the 16. Because you're getting close to the speed of light. It's like reaching a constant. So the energy is not changing much. But the relativistic form does change quite a bit because gamma is increasing ever more largely. And what we can conclude from this table, as we see that when we get to 99.99% speed of light, which requires 100 times more energy than the non-relativistic form, that ultimately it would take an infinite amount of energy to reach exactly the speed of light. So that's where the big difference is coming in on these two formulations, when you get close to the speed of light. Okay. All right, that will end this lecture, except with one parting thought, which is, since we see that it gets cumbersome to write the speed as 0.999 c, and to do it in your calculator to calculate these things becomes very cumbersome. You need a lot of significant digits in your calculator. It's best not to plug in numbers like that into your calculator when you get close to the speed of light. It's better in your equations, in your calculations, to work directly with the factor gamma. Gamma is 1 over the square root of 1 minus v squared over c squared. And using that instead of v will be much more kind on your use of significant digits in the calculator. Write your expression in terms of gamma, and so you just have to calculate gamma rather than working with v. All right, with that parting thought for practical use in doing calculations, let me end this lecture on kinetic energy.